Okay, the next part we're going to learn about, we've taken pressure into account, we have temperatures we understand a little bit. Now we're going to learn about wind. Wind is a force. It's basically air in motion. So let's see if we can learn a little bit about that. Oh yeah, one other thing. Wind is a vector. What the heck is that? It means it has speed and direction. So if I am defining temperature, I can tell you the temperature is 32 degrees. You got it. The pressure might be 29.75 inches of mercury. You know what that would be. But with the wind, if I just give you one value, I'm only describing a part of it. So if I told you the wind was 25 miles per hour, that tells me very little. I need to know what direction that 25 miles per hour of wind is coming from. So that's what a vector is. I need to know that it's northwest winds at 25 miles an hour. It could be southeast winds as well, and that would make a major difference in our weather. So it's a motion of air locally. So there are pushes and pulls on all objects anywhere in the atmosphere. So a force is just a mass times acceleration. We learned that with pressure. And we want to learn to apply the forces that actually control motion of air. So air pressure gradient. The atmosphere hates a pressure gradient, just like it hates a temperature gradient. So it's going to try to get rid of it. So the closer pressure lines are to each other, the more the pressure gradient is, the more the force is. There's something called centripetal force we'll talk about. Coriolis effect, kind of a unique force. Friction and gravity. So here's just a real simple example of pressure gradient. Pressure always flows from high pressure to low pressure. So if I have a pressure gradient that's very tight, think about if you were walking down a hill, you'd be almost running down the slope. If you were trying to go up that slope, you'd be having a much harder time. Well, if the pressure gradient is less, then it's easier for the air to flow. Less pressure gradient, slower, could be a walk almost to the air moving down the slope. So one of the easy ways to tell how the winds are going to be at your house is take a look at a surface weather map. If the air pressure lines are close to each other, watch out. It's going to get pretty windy. By the same token, if they're pretty far apart, probably won't have that much wind. Something that happens when objects move in a curve. Air is an object. A parcel of air moving in a circular motion. Why the heck is it staying in that circle? Well, there's something called centripetal force. It's like on a string when a person is trying to send a ball fast, or a slingshot moving around. When that slingshot is being held, that piece of object is being held there by the sling as it's spinning around, and when they release it, then it moves off straight. But while it's being held and can move in a circle, that force that's holding it there is called centripetal force. It's not independent. Tension on the string is responsible for that force. So it arises from an imbalance in other forces operating in the atmosphere. There's something called Coriolis effect. If we didn't have a rotating Earth, the atmosphere might behave a little bit nicer. But we do have a rotating Earth. So think about it. The Earth is rotating towards the east. So if I picked a point right here in the United States and looked at it a little bit later, and I compared it straight up on this 100 degrees thing, the northern position would hardly have moved. However, the other one would have moved a lot, actually producing a force to the right of the air motion, or the right of the motion of the particle. So in the northern hemisphere, the air is actually going to move to the right of its motion because of Coriolis effect. And it deflects more. Maximum deflection is at the poles. The minimum is at the equator. There is no Coriolis force on the equator. Friction is another one. Friction could be viscosity of a fluid when it's running over a surface. Say you hit the ground and a whole bunch of mountains are there. Well, the air is not going to want to move as fast because it's got to go up and down over those mountains. It's being slowed by friction. Another thing happens with turbulence in the atmosphere. Sometimes there's eddy motion that occurs with turbulence moving across areas, or maybe from convection, which we talked about earlier. That eddy motion, that turbulence, is extremely hard to define. But if you were to look at when you pour a little bit of cream into a cup of coffee or something hot, that cream goes in all different directions. That's turbulence. That's how it actually works in the atmosphere as well. So that is a part of friction. All of this, viscosity and everything, turbulence is all friction. Gravity just wants to pull the air down. Anything up and down is influenced by gravity. It has no impact on the horizontal whatsoever. So now we have talked about pressure gradients in the horizontal, and they could be in the vertical as well. Centripetal force, Coriolis effect, friction, and gravity. These are the forces that make wind. So let's just look at the vertical motion of a particle. Well, first, guess what? There's a heck of a pressure gradient in the vertical, isn't there? We've already talked that 850 millibars, for example, is what? About 5,000 feet up, maybe? So in 1 mile, we have a change of 150 millibars. We'll say from 1,000 being a normal pressure at the Earth, the surface. Think about it. If you went horizontally, you may never get that kind of a pressure gradient. So there is a tremendous pressure gradient on the air to try to push an air parcel up. Because remember, it's going from high to low. High is always at the surface. So that air parcel wants to go up. But what holds it down, what keeps our atmosphere in place, is gravity. So that is something called the hydrostatic equilibrium. An air parcel can still move when it's in hydrostatic equilibrium, but it cannot accelerate. So if there was convergence at the surface, it could push the particle up at a constant rate. If there was convergence aloft, it could push the particle down at a constant rate. Geostrophic wind. Now we're going to just take a couple forces here. We're taking the Coriolis force and the pressure gradient force. So pressure gradient force always acts perpendicular to lines of equal pressure. So you can see it here, always pointing from high to low. Coriolis force starts out pointing to the right. So it is deflecting this air parcel to the right, always. And eventually there's a balance reached. When that balance is reached, the air parcel, even though there's a strong pressure gradient towards low pressure, Coriolis is actually balancing that force. The Coriolis is dependent on the velocity, so that you wind up with an air parcel moving straight. That's geostrophic wind. It's a parcel in straight air motion. Gradient winds add one more thing. They have the Coriolis effect. They have the centripetal force as well as the horizontal pressure gradient. That centripetal force causes the air parcels to move in a circle. This happens around highs, around lows. Now, when you get close to the ground, friction becomes much more predominant. The closer you are to the Earth, the more friction plays a role. Friction is always going to be trying to slow the speed of an air parcel. So instead of having a faster air parcel motion, it's going to tend to be slower. So here for example, you have strong pressure gradient pushing towards low pressure. Centripetal force is acting to the right. And what happens when this air parcel would normally go in a straight line? It can't. Friction's slowing it down. which slows centripetal force, which causes the air parcel to start converging in towards low pressure or away from high pressure. That's why when you're at the surface of the Earth, you see winds blowing out of highs and towards lows. And you can see it here. There's a continuity to the air. It's all fluid. So if you have very fast winds hitting slower winds at the upper atmosphere, you're going to have convergence, causes sinking air, which is going to cause higher divergence at the surface. And the opposite is just true. Surfaces of the Earth. Take if you're going out over a lake. If you have wind blowing from the lake to the land, what's going to happen? The wind's going to hit the land, it's going to get rough, it's going to have friction, it's going to slow. What happens? The air parcels are going to be converging and they're going to be pushed upwards. Fluid, so it can't go into the ground, so they're going to push it upwards. That's a sea breeze or a lake breeze. That's what causes the clouds to form. If you didn't have that convergence, you wouldn't have the clouds. So let's just take a quick peek at a couple of these types of winds. Here's a surface weather map. Here is high pressure. And what do you see? The air parcels are moving out of the high. It's a pretty weak high. But you can see the air actually crossing isobars, moving towards low pressure down in here. Here's lower pressure up here. They're kind of moving towards the low pressure. And you can see the counterclockwise motion here. More of a clockwise motion here. If you go up in the atmosphere, same time, here is a gradient wind. Notice the circle. It's high pressure. And this is a gradient wind. And here, centripetal force causing the not being working on this part. This is actually straight line geostrophic wind. Again, here is centripetal wind. Notice how very parallel, if you had isobars here, you would find these are almost exactly parallel to the isobars. So, these are just examples of what you're learning this week. So, hope you got something out of this. If you have any questions, please don't hesitate to ask.